So now we're going to discuss the partial pressure of a gas. And the partial pressure is the pressure of a single gas in a mixture of gases. We can calculate partial pressure in one of two ways. First, if we know the mole fraction of that gas component in the mixture, and we know the total pressure. The partial pressure of gas 1 equals the moles of gas 1 divided by the total moles of all gases in the mixture. That's the mole fraction of gas 1. And we multiply that by the total pressure. And that'll give us the partial pressure of gas 1. Or we know the number of moles of the gas in the container, and we know the volume of that container, and we know the temperature of the gas. Then we can use PV equals nRT to calculate the partial pressure. P will be the partial pressure of that gas. Now, because gases act independently, remember they're very far apart. They're colliding with themselves, they're colliding with the sides of the container. The collisions with the sides of the container cause the gas pressure. And each gas in the mixture will contribute to the total pressure. So Daltons Law of partial pressures states that the sum of the partial pressures of all the gases in the mixture equals the total pressure. So the total pressure equals the partial pressure of gas 1 plus the partial pressure of gas 2, etc. for every component gas making up the mixture. So here's a question. Find the partial pressure of neon in a mixture with xenon. And it gives us the total pressure, 3.9 atmospheres, a volume of 8.7 liters, an absolute temperature of 398 Kelvin, and there is 0.17 moles of xenon gas. So how would you do this? Try and do it yourself, then come back and we'll go over it together. So first, use the moles of xenon, 0.17 moles of xenon, and the volume and temperature of the vessel to determine the partial pressure of the xenon. In other words, PV equals nRT. And the second thing is that the total pressure is equal to the sum of the partial pressures of the neon and the xenon. So once you know the partial pressure of the xenon and you know the total pressure, it should be pretty simple to just calculate the partial pressure of the neon by subtraction. Okay, so here we go. PV equals nRT. The pressure of the xenon is what we're trying to determine, times the volume, 8.7 liters, is equal to the moles of xenon, 0.17, times 0.082, and we're using 0.082 because we're going to calculate the partial pressure in atmospheres. The absolute temperature is 598 Kelvin, so the pressure of xenon equals 0.96 atmospheres. So, if the total pressure is 3.9 atmospheres, the pressure of the xenon we just calculated is 0.96 atmospheres, then we subtract the 0.96 from the 3.9 atmospheres total, and we get 2.9 atmospheres corrected for sig figs as the partial pressure of the neon. Now, partial pressure becomes a very important tool when we use a technique called displacement to measure a gas that we generate and the moles of the gas that we generate. This problem, we have 1.02 liters of hydrogen collected over water at 293 Kelvin with a total pressure of 755.2 torr. And the question is asking us to calculate the mass of hydrogen that we've collected by displacement. Now, when we collect a gas by displacement, especially in a situation like this here where we're using water as the media of displacement, we have to take into account that water evaporates and that some of the gas above the water is going to be water vapor. So when hydrogen is generated and bubbles into the container, it's not the only gas present. Water vapor particles are also present in this mixture of gases. So what we have to do is calculate the partial pressure of the dry hydrogen by subtracting out the water vapor pressure from the total pressure. So 755.2 is the total pressure of the hydrogen produced plus the vapor pressure. And so we first calculate the pressure of the dry hydrogen gas and then use PV equals nRT to calculate the moles of hydrogen and then convert moles of hydrogen to grams. Do you want to try doing this yourself and coming back? Let's see if you can do it. Then return to the video and we'll go through it. Okay, so here we're calculating the pressure of the dry hydrogen gas collected by subtracting out the water vapor pressure, 755.2 minus the 17.55 torr from water vapor. And now we have the pressure of the dry hydrogen, 737.7 torr. Now we can simply plug this into PV equals nRT. Here's the pressure, the partial pressure of just hydrogen gas that we just calculated. The volume of the container is 1.02 liters equals N, the number of moles, times 62.4 times 293 Kelvin. Solve for N, we get 0.0412 moles of hydrogen, and multiplied by the molar mass of hydrogen, 2 grams of hydrogen per 1 mole, to get 0.082 grams of hydrogen. There's the answer to this problem. And here's another application where we take an unknown metal, 2.61 grams of an unknown metal, and we react it with an excess of hydrochloric acid, and it turns out to be an active metal, which means that it reacts with a strong acid like hydrochloric acid to form hydrogen gas. And the hydrogen gas we collect by displacement. We displace 1.15 liters of water at 293 Kelvin, which is, of course, the volume of the gas generated, and the pressure is 1 atmosphere. Water has a vapor pressure of 17.55 torr at 293 Kelvin. Now assume that if we were to write out the chemical equation for this reaction, we would see a 1-to-1 mole relationship between hydrogen and the metal. That's very important. We're going to be calculating moles of hydrogen, but we want to be able to convert that into moles of the metal that reacted. And it's asking for the atomic weight of the metal. What's our target units? The target is atomic weight, which is grams per mole. 2.61 grams divided by how many moles we determine for the metal. First we find the pressure of the dry hydrogen. Then using PV equals nRT we find the moles of hydrogen. We convert moles of hydrogen to moles of unknown metal with a 1-to-1 relationship given by the problem. And we divide 2.61 grams of the metal by the moles of the metal. So what's the theory that helps us understand why we have these gas laws, why the gases behave as they do? Well, the theory is called kinetic molecular theory. And it's very simple. The particles of a gas, either atoms or molecules, are constantly moving, colliding with themselves, the walls of the container. There's no attraction between the particles. In a real gas, as the gas gets heavier, there are some attractions, and sometimes we have to put in a correction factor. But for an ideal gas, one that's behaving according to kinetic molecular theory purely, there's no attraction between the particles. When the moving particles hit another particle or the container, they don't stick, they don't lose energy, they can transfer energy, but they bounce off, they continue moving in another direction, like billiard balls, although billiard balls do eventually lose energy with every collision. Gas particles don't in this kinetic molecular theory. So there's a lot of empty space between the particles. The average kinetic energy of the particles is directly proportional to the Kelvin temperature. And as you raise the temperature of the gas, the average speed of the particles increases. Let's look at this video that shows how kinetic molecular theory works. In the middle of the 1800s, James Maxwell and Ludwig Boltzmann developed a statistical mechanical equation to describe particle speeds in gases, a statistical approach to kinetic molecular theory. As we have said, particles in the gas are assumed to be very far apart from one another, moving randomly in straight lines until they collide with another particle or with the sides of the container in perfectly elastic collisions. The Maxwell-Boltzmann distribution approaches this theory statistically, providing equations that plot the probability of gaseous particles moving over a range of speeds. In this computer simulation, developed by Professor Chpt at Brigham Young University, the x-axis represents the speeds of 100 gaseous particles, and the y-axis represents the number of particles with a particular speed, or the probability of particles found at a given speed. All of this at a given temperature. We notice right away that there is a whole range of speeds, from particles moving very slowly at the left side of the x-axis to particles moving incredibly rapidly toward the right side of the x-axis. We also notice that the numbers of particles, or probability of the particles at these extremely slow or fast speeds, is very small, and that the highest number of particles move at speeds near the average of all particle speeds, near the top of the curve generated by the probabilities at all speeds. Look at the shape of this curve. It is not symmetrical. It rises steeply in the beginning, then proceeds to broaden out after the apex. What would happen if we added 100 particles of another gas to this container? The increase in the number of particles would also increase the number of collisions on the sides of the container, with each collision imparting a force to the container wall at the point of impact. Since the number of collisions per unit area would increase, the pressure on the container wall would increase also. Pressure is measured in units of force per unit area, for example, pounds per square inch. Let's now use another simulation to show what the distribution would look like if we strongly heated the gas. This simulation, by Rapp and Walter at the University of Pennsylvania, shows the probabilities of particle speeds over time eventually generate the Boltzmann distribution curve, here depicted at 100 Kelvin. What would the curve look like at 500 Kelvin? Let's try it. We notice that the curve has flattened out and broadened, and the average kinetic energy, as one would expect, has increased. Now the particles are moving, on average, more rapidly, and they strike the sides of the container more frequently and with greater force. This increases the pressure of the gas within the container. So now let's look at gas properties and the gas laws in light of the kinetic molecular theory. First of all, how about the indefinite shape and indefinite volume of a gas? Well, because gas particles have enough kinetic energy to overcome attractions, they keep moving around and spreading out until they fill the container. And as a result, gases take the shape and the volume of the container that they're in. And gases are compressible. There's a lot of empty space between gas particles, and so you can squeeze gas particles together. Now, what about Boyles Law? How would you explain that? Well, Boyles Law says that the volume of a gas is inversely proportional to the pressure. Decreasing the volume means that the particles don't have to travel as far before they hit the sides of the container, so that there are more collisions with the sides of the container. Now, the velocity of the gas hasn't changed. The kinetic energy of the gas hasn't changed because we haven't changed the temperature. But the particles are hitting the sides of the container more frequently, and that increases the pressure within the container. Now, what about the low density of a gas? Well, because there's a lot of unoccupied space in the structure of a gas, gases don't have a lot of mass in a given volume. So they have a low density. And we usually express the density of a gas as grams per liter rather than grams per milliliter or grams per cubic centimeter as we do for a liquid or a solid. Now, what about the effect of temperature? We saw before how temperature and pressure are related, and insofar as temperature affects pressure, the volume is also a player as well because volume affects pressure. Charles's law says that the volume of a gas is directly proportional to the absolute temperature. So increasing the temperature increases their average speed, causing them to hit the sides of the container more frequently and with greater force. So in order to keep the pressure constant, the volume must then increase. Now, we also know about Avogadro's law. It says that the volume of a gas is directly proportional to the number of gas particles. If we add more gas particles, then there are going to be more collisions of gas particles with the walls of the container. And if you're not going to allow the pressure to increase, you've got to increase the volume so that the pressure remains constant. And what about Dalton's law of partial pressures? How does kinetic molecular theory explain that? Well, Dalton's law says the total pressure of a mixture of gases is the sum of its partial pressures. Kinetic molecular theory says that gas particles are negligibly small and don't interact. Therefore, the particles of a gas behave independently of each other, each gas contributing its own collisions to the container with the same average kinetic energy. And since the average kinetic energy is the same, the total pressure of the collisions is the same. Now let's reinforce the Boltzmann distribution model that we saw in animation before. Here we have two profiles, one for oxygen gas at 25 degrees and another at 700 degrees. And what you should realize, the oxygen at 25 degrees rises steeply and has a lower kinetic energy on average. This dotted line represents the average kinetic energy. As you can see, the average is near the apex of the Boltzmann curve. If we heat up the oxygen gas, what happens? The curve becomes lower and broader. It broadens out. So at 700 degrees, the average kinetic energy has increased quite a bit. Now, here's an incredibly important concept. The kinetic energy at a given temperature is the same for all gases. It doesn't matter whether you're talking about oxygen or hydrogen. If you're talking about kinetic energy, not speed, but kinetic energy, then oxygen and hydrogen have the same Boltzmann curve distribution. At 25 degrees, it's the blue. At 700 degrees, it's the red. That works for oxygen. That applies to hydrogen. How can this be? Well, kinetic energy is equal to 1/2 mv squared. You all know that. And gas particles at a given temperature have the same curve. The same curve, regardless of what gas you're talking about. So if hydrogen gas and oxygen gas are both at 25 degrees, then what has to be true? Are their velocities equal? Are their velocities different? If the velocities are different, how are they different? Again, look at Ke equals 1/2 mv squared. The mass of the oxygen is much heavier than the mass of the hydrogen. But 1/2 mv squared for each gas, the kinetic energy, in other words, for each gas is the same. So if the kinetic energy profile for each is the same, but their masses are different, what does that tell you about the velocity? It says the velocity has to be different as well, such that their product, after you square the velocity, is going to give you the same value for kinetic energy. So the lighter the gas is, the smaller its mass is, and to make up that, the velocity of the lighter gas has to be greater, such that mass times the square of the velocity times 1/2 equals the kinetic energy. So again, the kinetic energy profile for both of these gases is identical, but they don't have equal masses. Hydrogen is much lighter than oxygen, and therefore the velocity of the hydrogen is much greater than oxygen, such that 1/2 mv squared for each equals the same value. Here is an experiment often used to demonstrate this point. You have a glass tube, and cotton balls are used, and one cotton ball is soaked with ammonia. Ammonia has a mass of 17 grams per mole. The other is soaked in hydrochloric acid. HCl has a molar mass of 36.45. So the HCl is roughly double the mass of the NH3 gas. So both of these, although they're in solution, they're outgassing ammonia gas and hydrogen chloride gas. And when the fumes commingle, there's a reaction as the substance ammonium chloride, NH4Cl, forms. That's a solid salt, not a gas. And what happens is that you get a white ring around the sides of the tube where these gases commingle. So take a look at the way this is happening. The ring is closer to B than A. Can you identify which side has the hydrochloric acid and therefore outgassing hydrogen chloride, and which side the ammonia? Is side A HCl, side B ammonia, or vice versa? So what we've been talking about is the process of diffusion. That's when you have a collection of molecules spreading out from an area of high concentration to an area of low concentration. But we can also talk about the process of effusion, and that's the process by which a collection of molecules escapes through a small hole into a vacuum, and that's called diffusion. Now, for gases at the same temperature, the rate of gas movement is inversely proportional to the square root of the molar mass. And that's understandable now because you know Ke, kinetic energy, equals 1/2 mv squared. So you see that mass is there, and then the square of the velocity is there. So if you make a proportion between the two, the rate will be proportional to the inverse of the molar mass. In other words, just as we had noted before, the heavier the molecule, the slower it goes. And that's an inverse relationship, but it's to the square root of the molar mass. Graham's law of effusion states that for two different gases at the same temperature, the ratio of their rates of effusion is given by this equation. The rate of gas A over gas B is equal to the square root of the molar mass of gas B divided by the molar mass of gas A. So we can do a problem now. An unknown gas X effuses at 0.462 of the rate of nitrogen gas at the same temperature. Calculate the molar mass of this gas. Well, the first thing we want to do is read the problem and convert that into some kind of mathematical expression. So translating that mathematically, it's the same as saying the rate of gas X equals 0.462 times the rate of nitrogen gas. Now we can make a ratio of the rate of gas X over the rate of N2 equaling 4.62. So the rate of gas X over the rate of N2 equals 0.462. And we're now able to state our Graham's law of effusion ratios. Rate of gas 1 divided by the rate of gas 2 equals the square root of the molar mass of gas 2 over gas 1. So putting that in terms of this problem, the rate of gas X over the rate of N2, which we know, by the way, is equal to 0.462, is equal to the square root of the molar mass of nitrogen over the molar mass of gas X. Oh, you see where this is going? Working it out, 0.462 is equal to the square root of 28 divided by the molar mass of our unknown gas. Working it out, we get the molar mass of gas X equals 28 divided by 0.213, and that's going to be 131. So there it is, finding the molar mass of a gas from Graham's law of effusion. Well, so far we've been talking about ideal gases, and ideal gases behave according to the equation PV equals nRT. That's an ideal gas. Not all gases behave as they should, either because of attractions between the particles. They tend to be sticky particles. So, of course, the assumption is there are no attractions between particles in an ideal gas. Some gases do have attractive forces. And the other is the actual size of the molecule that comes into play at high pressures. It begins to be a contributor to the volume of the gas when you have so many particles squeezed together at high pressures. So there are two conditions when you get noticeable deviations from ideal gas behavior. Okay? One is at higher pressures. When you have higher pressures, you have a lot of particles squeezed together, and that begins to set up attractions between them, and the volume of the particle is no longer negligible. And at lower temperatures, also, gases will deviate from ideal gas behavior because they're moving more slowly. That allows attractive forces to be set up between them. So, one way we can show this deviation from ideality, how real gases behave, is to plot PV over RT versus the pressure for 1 mole of a gas. And that is very good at showing the difference between a real gas behavior and an ideal gas behavior. And it shows a curve for a particular gas that shows the PV over RT ratio for a real gas is generally lower than ideality for low pressures. Meaning, if the pressures are low, the most important factor is interparticle attractions. And then at higher pressures, you begin to get deviations that are greater than what you'd predict ideally, because the important factor becomes the volume of the molecule. So let me show you an interesting graph. Here it is, PV over RT plotted against pressure. Now, just think about this for a minute. If you have 1 mole of a gas, so PV equals nRT, right? You have 1 mole of a gas. If you solve for the mole of a gas, 1 mole of a gas, you will have PV over RT. In other words, PV over RT should equal exactly 1 for an ideal gas. And when gases deviate from that 1, they begin to show behavior more like a real gas than an ideal gas. Now here's what it was talking about. At lower pressures, we see water has quite a bit lower value of PV over RT than an ideal gas. So does xenon, this green line. And that's because water is well known for its stickiness, its attractions between particles. And ideal gases aren't supposed to have any attractions between particles. The green xenon line also shows attraction. Xenon is a noble gas, but it's a heavy noble gas, and it too deviates from ideality at lower pressures. Now, what happens as we increase the pressure? The water begins to swoop up, the xenon certainly begins to swoop up, and most of the other gases that are lighter definitely show deviation from ideality. That's because at these high pressures, you're squeezing the particles really closer together, and their volume is no longer negligible. And that's why these particles deviate from ideality. Okay, here's a question I love to ask. I'm not going to solve it for you, but I'm going to tell you, you probably will see this on a quiz or test. 75 milliliters of helium gas at 722 torr. Well, not this exact problem, right? 75 milliliters of helium gas at 722 torr. It's isolated in one of 2 interconnected but sealed containers. And in the other one, you have 230 milliliters of argon at 945 torr. So what's the pressure when you open the valve? And I'll give you a nice big juicy hint here. When you open the valve, what does the new total volume for both gases become? Okay, so now temperature is not a player here. It's just P old V old equals P nu V nu. And you've got an old volume, and then you've got a new volume for each gas. Like I said, you'll see it again. Okay, that completes Chapter 5B, a video on 5B.